Okay, so let's make a start for today. Before we start the lecture, just to let you know, just in case you didn't, the seating list for the midterm, which is on Monday evening at 8 o'clock, is on IVLE, so you can check where you're supposed to be sitting and so on and so forth. I'll leave you to read that for yourselves. Just a couple of notes from the end of last lecture. So if you remember, it's almost 2 weeks ago now, we were talking at some stage about Gaussian tables, basically tabulation of the distribution function for the Gaussian. And basically the tables look like this. So, for example, what they do, they compute. So you're given a value of the random variable along this x-axis, so we call that little z. And what this table does is computes the probability or the area under the curve to the left, i.e. this value of the CDF. So for example, if you give me the value z, which is 0.5 for the standard Gaussian, then the probability that you're less than or equal to 0.5, the probability that you're less than or equal to 0, is 0.5. Similarly, if you're interested in the value z is equal to 0.04, okay, so this is 0.04, then the probability that you're less than or equal to 0.04 is 5160, and similarly, if I want to go to another thing, I give you the value of z, which is 1.96, okay, and I have the probability that I'm less than or equal to 1.96 is 0.975, okay. So this is how you use this table. Where was I? You could also compute the quantiles. So this is another table which we have in our notes. So what this does is it gives you the value of the area and then the associated value of z, which generates this area. This is a one-to-one function. So for example, if you give me that the area under this curve is equal to 0.5, then the point, the largest point which this is possible for is z is equal to 0. And so, for example, if I'm interested now in a very big probability, let's say 0.95, then basically this value here would be on the x-axis would be 1.645, and so on and so forth. Okay, so this is how you read these Gaussian tables. It's very straightforward, I think. Okay, so that's taken us, just a few minutes. So where have we reached in the notes? So we're up to chapter 5, and we'll take a gentle stroll through chapter 5. We have some additional notes I've added today as well, which we will discuss later on. And so this chapter, which is the fifth of 9, is on sampling and sampling distributions, and is really the notion that you have some concept that there is some overall population, for example, the population of Singapore or something else, and what we're interested in doing is studying this massive population of things, in my example, people, and trying to understand, based upon a subset of this information, what could be said about the overall population. Okay, so that's really what this first part, at least the first part of the chapter, is all about. So you can see a variety of topics. There's not much point of talking about all of them. Most likely we won't get any further than this one today. So we're going to talk about populations and samples, random sampling, and potentially the sample mean distribution of the sample mean. And in between there, we're going to talk about how to estimate some parameters of statistical models somewhere around at this point. Okay, so this is basically this introductory slide is exactly what I'm talking about. So the idea is that you have the totality of all possible outcomes of observations of a survey or experiment is called a population. So generally this underlying information, this population, is too large to work with in practice. So as I said, if you're interested in characterizing the average height of everybody here in Singapore, it's unlikely, maybe these days you have census information, but it's pretty huge if you wanted to do that for yourself. Let's say you just wanted to do an experiment. So what you could do is to take a subset of the population and try and study that because it's more feasible. Okay, and that's basically what we're going to talk about for this part of the notes. So a sample is basically a subset of a population. So a population is basically the totality of all possible outcomes. This shouldn't be confused with the concept of probability spaces, where we've moved away from that now. So the key point is this, is every observation or outcome can be recorded as a numerical or categorical variable. At least in our world, that is the case. So there could be heights, there could be weights, there could be things like that. And each member of a population is a value of this random variable. Okay, so we're talking about the random variables that we discussed a while back. Okay, and we're interested in two types of population, which are finite and infinite populations, and we're going to see examples of each as we progress through today's lecture. So a finite population, as one might expect, it consists of a finite number of elements. For instance, it's all the citizens in Singapore, that's a finite number. All the books in the science library, basically anything which you can count and you get up to a number which you know is an integer, is basically something which is a finite population. Okay. And despite the fact that you have finite populations, there can often be too big to work with. Another example, or the other example that we work with, is infinite populations. So an infinite population is one consists of infinitely many outcomes. This could be countable, though. You could have a countable number of outcomes that just happen to be infinite, or they could be uncountable. Typically, we don't work with uncountable samples. It doesn't make sense for us, but countably infinite samples do occur in practice. So examples of such types of populations, which one might want to study, the results of all possible rolls of a pair of dice. Okay, so what does that mean? That's actually not very well phrased. What it is meant that you take a sequence, so you roll, and you have basically an infinite sequence of a pair of dice. Okay, that's obviously an infinite population, although admittedly not very exciting. If you take random digits from replacement from this sample of 10 digits, okay, so you know there is a countably infinite number of random digit numbers that I can take from this. Okay, the depths of all possible conceivable positions of a lake. Okay, this is something which is continuously monitored, and obviously therefore is a continuous variable, and thus has a cardinality which is infinite. In practice, some finite populations are so large that basically we assume them essentially to be infinite. So the population of lives of a certain type of storage of a battery could be such an example. It's so big that we just basically treat it as so that we can't deal with it. Okay, so let's talk about, so the idea now, what are we trying to do? Well, we want to basically construct subsets of these big populations in order to do things which are useful. So later on today we're going to talk about how we can take subsets of data to estimate parameters of statistical models, and I'll talk about that in a moment. So the idea is that we have something which is called random sampling, and the idea of a simple random sample is as follows. So you have a collection of n observations taken from a given population, which is called a sample of size n. Okay, so basically you have a population, could be 1 million things, and you take n of them, where n is perhaps often much less than 1 million in my example. And each observation in this population can be considered as a value of a random variable which has a certain probability density, okay, or distribution. This is not. Remember, we're using capital F for distribution functions. This is a density function, typically PDF. And so a simple random sample, okay, is simply this. It's a sample in such a way that every subset of n observations of the population has the same probability of being selected, okay. So we have n things, and let's say we have capital N things, if it's finite, and we want to choose little n things from that. And if the chance of any subset of size little n has equal probability to occur, then we call this a simple random sample, okay. So let's see a couple of examples, although I don't think this is a particularly useful example. So you've got 20 mice and you want to choose 5 of them. basically what you want to do, how can you get a simple random sample from this? Well, basically you can choose any of the 5 mice with equal probability without replacement. Okay, so here this is an experiment which uses Excel, but there's a lot of ways that you can do this. All this information is telling you is that basically you've got, let's say you number the mice 1 to 20, and you pick a mouse with probability 1 upon 20. So you've chosen one, you've got 19 mice left. Now you want to choose one of the other 19 remaining mice with the probability 1 over 19, and so on and so forth. And so in this scenario, the chance of choosing a given sample of 5 distinct mice is precisely equally likely no matter which the mice are. Okay, this is what it says. So again, you have 5, let's say you've got 5 mice. Mouse number 1 is chosen with probability 1 upon 20, and it could be so that's equally likely that any of the mice were chosen. That leaves me with 19. Now I'm going to choose another mouse with probability 1 over 19. That gives me 18 left, and so on and so forth. This is what this code will do here. Okay, and that's it. I mean, this is not, it's no more complicated than that. Okay, we can move on. Okay. So let's talk about this. So that was an example actually of a simple random sample from a finite population, and we're going to see a little bit more of that now. So if we're given a population of 4 things, here we're going to say they're A, B, C, D, then, and we want to take 2 of those individuals, 2 of those things from the set A, B, C, D, then there are 4 choose 2 possible samples of size 2. So here we don't care about the order, so we don't count AB and BA twice, for example. Okay, so this is our 6 possible samples of size 2. So A with B, A with C, A with D, B with C, B with D, C with D. Okay, and that's our sampling without replacement from this finite sample. And so my example, or our example in the previous example, was actually sampling without replacement as well. So in general, if you have capital N elements of the population and little n points are taken from capital N, so little n is taken strictly less than or equal to capital N, because it's sampling without replacement, then of course there are capital N choose little n possible samples, okay, that you can take. Right, of size little n, right? Just as you have here, 4 choose 2, in general it's capital N choose little n, okay? And if it's a random sample, so a simple random sample without replacement, is then basically each sample has probability 1 over capital N choose little n chance of being selected. Okay, so that's the chance of choosing each sample. You can check for the mice example, you get this as well. Okay, I was talking about individual mice there. Okay, so that's how you construct a simple random sample without replacement from a finite sample. You can also sample with replacement. So this is more complicated, right? Because basically now the order does matter, because you can pick A twice, for example. I can pick A then B, but I can also pick B then A, and B then A is a different sample than A than B, right? So here now, instead of having capital N choose little n possible subsets of size little n, in this case we have 4, and we're going to take 2 out of them. So every time I sample an individual, there are 4 choices. So there are 4 times 4 possible samples I can get. It's 4 squared, 16 samples of size 2 in my example. Okay, and so you can imagine in general, if you have capital N points and you choose little n from those capital N, then there are capital N to the power little n samples with replacement. Okay. So this is the example here. So now the order counts. So yes. So here the order, so as I said, I've just stated why that's the case. So in general, capital N to the n, capital N to the little n is the number of samples of size little n that can be drawn from a finite population with size capital N with replacement. Therefore, basically each sample has size 1 over capital N to the n of being selected. Okay, that's sampling from a finite population with replacement. Okay. Now let's think about the case of, so this is leading somewhere, so don't think that I'm just telling you nonsense. We're going to use this for something. So if you want to sample now from an infinite population, when you have a list available and items are readily numbered, it's basically easy to draw random numbers from finite populations. But in the case when you have an infinite population, it's basically impossible in some sense, right? I mean, you have, for example, you want to have representations of the depth of a lake. I mean, you can't just take very easily samples of depths of lakes. So basically the concept of a random sample from an infinite population is much more difficult to understand, and we're going to look at some examples basically to see how we can construct such cases. Okay, so let's have a look at this example. So you have a sequence. So if you have the results of 15 flips of a coin as a sample from a hypothetically infinite populations. So what does this mean? This first statement, what it means is that basically you have an infinite sequence of flips of coins. Okay, this is actually kind of a routine thing that one does in probability, but it's not important here. Okay, so you have an infinite flip of coins. You just take 15 flips. Okay. Now, if the probability of getting heads for each flip, if the probability of getting heads for each flip and the 15 flips are independent tosses, if you like, then what we're going to say is this sample is random. So what we're going to say is a sample is random. So if you have an infinite sequence of random variables, and if you can take an independent and identically distributed sequence of finite sample size, then we say that the sequence is random. So it's basically random samples and IID sequences are equivalent, and we're going to see this more formally slightly later on today, quite soon in fact. Okay, so let's look at another example. We'd also be sampling from an infinite population if we sample with replacement from a finite population, and our sample is random if, firstly, in each draw, all elements of the population have the same probability of being selected, and each successive draw is independent. Okay, so this is an example of what we call so what this says is basically you have a population infinitely, right? You choose a position, we draw any element of this population with equal chance, and then successive draws are independent. Again, another independent and identically distributed sequence. Here, this is another one, which is perhaps it makes it more obvious. So we consider the population of the sums of all possible rolls of a pair of dice. And what that means is that you roll a pair of dice and you do that infinitely often. So you keep on doing it. You start today and you keep on going well beyond the end of the earth. So it's an infinite number of rolls. Okay, so an infinite sequence of rolls of pairs of dice. Okay, so this is of course an infinite sequence, and so the population is infinite. Okay, so now what we're going to do is we want to choose a random sample of size n from a random variable x. So basically now what we have is we have this infinite sequence, and we're going to take a subset of that sequence, which is finite length. Okay, and each random variable in this sequence is going to be having the following probability mass function. So this is a fair dice. So okay, so I can roll a 1 with probability 1 of 1/6. So the probability that I roll I get 2 is the chance that I get 2 1s, and that's 1 over 36. The chance I get a 3 is if I get a 2 or a 1. Okay, and there are two ways of doing that, so that's 2 over 36, and so on and so forth. The x is 12 with probability 1 over 36, I have to get 2 6s, and so forth. Okay, so this is just a probability mass function associated to rolling 2 dice and adding together the scores. Okay, and so what we're saying the population is an infinite sequence of these random variables which possess exactly this probability mass function. And what we want to do is we want to study this infinite sequence by taking a finite subset of this infinite sequence. It's a random sample of size n, which means basically we independent and identically distributed random variables from this thing. So to obtain random samples of size 100, all we simply do is we could just roll a pair of dice 100 times independently under the same conditions up to some epsilon. And if xi represents the result on the ith roll, then we have x1 up to x2 up to x100. Okay, so this is our random sample. Okay, so in this case, as we've said, all these random variables x1 up to x100 are independent and they're identically distributed. We know the random and we know the probability mass function for each of these random variables. So if I want to know the joint distribution of this random sample, okay, so that's the probability that capital X1 is equal to little x1 all the way up to capital X100 is equal to little x100, okay, they're all mutually independent. Okay, so their joint probability mass function is equal to the probability of each of their individual mass functions, of each of which has this representation. And that's obviously, this is just a product notation. So what this means is the product I is 1 to 100, the probability that capital Xi is equal to little xi. So this statement in this middle line is exchangeably equivalent with the product notation on the line below. Okay. So this is a joint distribution of this finite sample. Okay. Yes. Okay. So this is the, let's have a look at this definition. So we have a random variable capital X with a certain probability function. It could be a mass or density function. So now we take a finite sample of these random variables, x1 up to xn, which has the same distribution as x. Then x1 up to xn is a random sample of size n from a population with distribution f if they're independent. Okay, so they're all independent. And the joint PDF or PMF is just equal to, so the joint PDF is just the product of the individuals. Okay, so this is the theoretical x we're interested in, and we take a random sample to represent this random variable, and we can express the joint PDF. Okay, so before we go any further, I don't find this next part really very well linked to the rest of the notes. So I'm going to tell you something about why this is useful. I think this might make it more transparent than the main lecture notes, because I don't get a lot out of this. So if you like, this is going to explain to you why what we've just been talking about for the last 20 minutes is of all interest. And it's something called maximum likelihood estimation. It's not going to be on the exam, but I think hopefully it will make the whole part of these lecture notes much more clearer, because they don't look very understandable otherwise, at least not to me from the beginning. Okay, so don't worry, we're not going to see this in the exam, but I think, yeah, as I say, you just want to see why it's useful. So kind of the applications of this notion of a random sample is in the estimation of parameters. So we've seen frequently probability density functions and probability mass functions, such as the Poisson, this is my minor modification of the notation, or the Gaussian. But we've never really worked out what are these parameter values, right? You can choose mu, and to remember that the Gaussian distribution has a mean and a variance. I could choose any mean and any variance, and if I'm trying to summarize some particular collection of random variables or a given random variable, it's obvious that some mu and some sigma squared are better than others. Okay, and so this is what we're going to do, is we're going to use the notion of a random sample to determine the associated parameters of the probability model. Okay, and basically it's very important actually. I think none of us think you should learn a course on probability and statistics without knowing what this thing is. It's called maximum likelihood estimation. Okay, so this is the idea. So you have, as we had in this previous definition. So this definition says I've got a random variable x, it has a probability distribution f. Okay, and now what I want to do is I'm interested in this variable, but I'm just going to summarize. I'm going to get samples or data associated with this random variable, and on the basis of this random sample, which is of size little n, I'm going to then correspondingly calculate what are the associated parameters of the statistical model which I was originally interested in. Okay, because basically if I know this if I know this probability mass function, okay, so I can hypothesize a family of probability distributions such as the Gaussian or the Poisson or whatever you like, depending on the associated properties of the data. But to actually know the associated parameters which are generating this random variable x are basically to allow one to perform some sort of inference with respect to x. For example, to estimate what is the value of x if I don't know what it is. Typically I don't. Okay, so we observe data or points. Okay, so this is what you'll see in real statistics. You see some data. Here we can be real values, real numbers, x1, x2 up to xn, but any sequence of random variables which are having a joint distribution. Okay. I'm using a subscript theta. Okay, so what does this theta mean? This is the unknown parameter. So for example, in the case of the Gaussian, the theta represents a bivariate vector mu and sigma squared. In the case of a Poisson distribution, it's the unknown rate parameter lambda. So remember, the mean of a Poisson, which is the same as the variance, is its parameter lambda in our parameterization. So the idea of what maximum likelihood estimation is to try to work out, as I said, the parameter of the associated model which is most consistent with the data we observe of the random variable of interest. So going back to our main lecture notes, capital X could be, for example, the weight of, I don't know, alligators across the world or whatever you like, right? You can think of whatever you like, right? So, and basically, if you say, okay, the weights are something like Gaussian distributed, I think that they could be Gaussian distributed. You hypothesize that as a model, okay? Then you go out and collect some weights of alligators. Let's say we can get the weights of 10,000 alligators. And then we're going to try to work out what are the associated parameters of our probability model on the basis of those 10,000 observations of weights of alligators. You see what I say? It could be anything. I just came up with alligators. I suppose I saw an alligator before I came to the lecture. Okay, so the way in which this is constructed is to basically find an estimate of this parameter theta, which is most consistent with the data. Now, what does that mean? In our language, what that's going to mean is you have the joint PDF or PMF, okay, that's going to be formed by the associated probabilistic structure of the random variables x1 up to xn. So in our case, x1 up to xn are IID. So we can easily write down the joint PDF or PMF, we will do in a moment. And then what we're going to do is, on the basis of our realized value, our data, we're going to maximize the chance of seeing our data. So basically, if you think, sorry, I'm trying to just highlight this F, right? If you think about this quantity, what this represents, suppose x1 up to xn, or the random variable x, is a discrete random variable, okay? Then what this quantity represents is the probability of seeing our data, okay? And so the mechanism that we're going to employ is to find the parameters which maximize the chance of seeing our data, okay? This is the idea. And of course, for those of you who are more mathematically inclined, you will have to ask the question, does such a maximum exist? And the answer is, well, not always, but at least in what we're going to look at in this example, this short part of the lecture notes, we will see specifically that there exists a solution of this problem. Okay. Okay. So basically, how does this proceed? So this is really, all this section is designed is really to explain the significance of this slide. Okay, that's what I'm trying to do, because I don't find it very clear otherwise. I mean, maybe you do, but that's good. But if not, I think that this will make it very clear. So what we're assuming is our random variables, our sample is we have a random sample. Okay, so in the notation of the lecture notes. Okay, so x1 are mutually independent, and we're assuming they have the same distribution. So we're going to use this notation that the random variable capital X subscript I is independent and identically distributed and has some distribution f theta. Okay, so that is to say that the joint PMF or PDF, depending on the nature of those associated random variables, is just simply the product of the associated component PDFs or PMFs. Okay, so this calculation here, it's identical to this one here. Okay, this was an example where they happen to be X, the random variables happen to be the sums of pairs rolls of dice, okay, but this is equally true if these random variables are jointly continuous or discrete, doesn't matter. This is always true. Okay, and remember, just in case, that this product I is 1 to n of this thing is just a shorthand for this term you see towards the left, on your left. Okay, so basically there is a terminology which is used in statistics that this joint PDF or PMF of the data is called the likelihood of the data. Okay, so just as I told you before, if the random variables x have to be discrete, what this function corresponds to for a given theta in a given data set is how likely we are to observe the data. So obviously what we're doing is, the point is, in this context, we know the data, we know x1, we know xn, we know x2, but what we don't know is theta, because if we knew theta, I mean, somehow there's not much to do, right? If I know the parameter associated to my random variable of interest and somehow the problem is solved, I can go and do my probabilistic calculations, for example, as we've seen previously. I can compute probabilities associated with the random variable, but otherwise I can't if I'm assuming that my model is intrinsically parametric, and so we have seen examples, 2 examples before. Okay, so I'm just going to tell you roughly now basically, hopefully that's explained the significance of the slide. Excuse me. But now we've understood the significance of this slide, let's at least finish the explanation. So this is just more of the slide. You're not going to have to do these calculations in your examination, but I really think that if you don't learn maximum likelihood estimation now, if you haven't learned it before, you should learn it someday. So you have it in the back of your mind, especially for future courses. Okay, so how do we do this mechanism? So this is just an aside, really. I mean, so the idea is I want to maximize this function, right? This function is a function of the unknown parameter theta. It could be in r to the 2, r3, r4. Obviously, the dimensionality of the unknown parameter gets bigger and bigger, so the problem gets more challenging and challenging. Okay, but of course, in our short excursion into this area, we're only going to talk about the notion where theta is a real value. Okay, so if you didn't know this, don't worry, but I'm just going to tell you as a fact. If I want to maximize this function as a function of theta, I can take any monotonic transformation of it. So monotonic function is one which is non-increasing or non-decreasing. Here we're monotonic increasing we want to take. So if we take a monotonic increasing transformation of this and maximize that, it's exactly the same as maximizing that. So what I'm saying, so this is what I'm talking about. I'm just talking about this sentence here. And why am I talking about it? Well, I'm talking about it because basically in this particular class of problems, it's because you have this product, okay? And sometimes, if you imagine in today's world, n could be very large. You could have 10 billion data points, right? There's big data, some of the things you should be learning about in other courses. And if, for example, if I want to even evaluate this function for any given theta, well, for 10 million points or 10 billion points, I can still do that. I can definitely do that today. But the point is that the number, this product, is basically going to be 0, or it could be, or infinity is going to blow up, or it's going to go to 0. Normally, these type of functions do. So from a computational perspective, and actually, as it turns out, a mathematical operation, it's more convenient instead to work with working with this function, but it's just to take the logarithm. Okay. So what we're going to do is to work with the what we call the log likelihood. So this is the likelihood function. So I just take a logarithm. This is a natural logarithm. Okay, log to the base e. Just in case you're wondering, I use log for log to the base e. This is convention in mathematics. Okay, and because this is, remember that this function f sub theta is the product I is 1 to n of f sub theta. Okay, so the logarithm of a product is the sum of the logs. Okay, so I just recur. So so for two real numbers, non-negative, less positive numbers a and b, the log of a times b is log of a plus log of b. Okay, so now if I just take the logarithm of this, then if I apply my formula once, logarithm, I get the logarithm of f theta x1 plus the product I is 2 to n of f theta sub fxi. If I do that now further n minus 1 times, I will get that the log likelihood for my random sample of data is just the sum I is 1 to n of the logarithm of the density function for one data point evaluated at theta. Okay. Right, now what do I want to do now? So now I want to find the maximum likelihood estimate. So I want to maximize this function with respect to theta. This is just pure optimization, which you probably studied. You must have done A-level math or the IB in math or something like that. I don't know how the IB works actually, but I suppose it's a mathematical component. So all I want to do is I just want to maximize this function, okay? And it's fairly straightforward if theta is continuous, as it almost always is. So in our example, for example, if they have a Poisson random variable, this parameter lambda is positive. So that's a number which is 0.001 or 10 million or something like that, but it's a number, right? So this is a continuous thing that I want to calculate. So assuming that this function is differentiable in theta, all I need to do is I need to differentiate the function, solve when the function is equal to 0, and then that will give me my maximum likelihood estimate if the second derivative is negative. Okay, you don't need to know these things now, but I hope you've learned these once before. Okay. If theta is a vector, what you do is you compute what's called the gradient vector, and that's just a vector of partial derivatives. So that it looks like, don't worry, we're only going to take the case where d is 1, but in general, in our example. But basically, just differentiate the function with respect to theta 1, then you differentiate the function with respect to theta 2, all the way up to the derivative with respect to the dth variable. Okay. So, of course, we're assuming the function is differentiable in theta, so this again is another assumption which, whether it's true or not, it depends on the case of interest. And now to maximize, of course, what we want to do is we want to find the root. Okay, we set the derivatives equal to 0 and solve. And then if you want to check if it's a maximum, okay, so there has to be, now, so we can see a lot of things. So first of all, I have to be able to differentiate the function, then I have to be able to solve this equation equal to 0. Okay, and then what I want to do is I tend to check if it's even a maximum. So typically, in optimization theory, you can do that by checking whether or not the Hessian matrix, it's just simply, if you want in dimension 1, it's just the second derivative of the function, is negative evaluated pointwise at the function. So if you like, you can read this point. This is basically the Hessian matrix, and you have to check if the eigenvalues are all negative, and you don't know anything about that. It's not important. No one will ask you in the exam. Okay, so the scheme of maximum likelihood estimation, okay, this again, I'm just clarifying why you would be ever interested in a random sample, and this is why you would be. It works as what follows, right? You compute the likelihood function. Okay, when I say compute, I don't mean evaluate on a computer. You just write down on a piece of paper the product I is 1 to n of the density function evaluated pointwise at the data point, i.e., what I mean by that is this function here. Okay, then the second step is you compute the logarithm, okay, and you differentiate it. Okay, now once you've differentiated it, you solve the equation with respect to theta, that the derivative of the log likelihood is equal to 0. Okay, so you're solving with respect to theta. If there exists a root of that, of course there may not be, or it may not be an analytical one. Okay, that's a potential solution, so we're assuming there's only one at this moment. And then what you want to do is you want to work out if that's a maximum or not. And so all you need to do is just differentiate this function one more time and substitute in the value theta n tilde into this function. And if it's negative, you have a maximum, global maximum. And of course, there are many caveats, okay, to what I'm talking about. So of course, one is that I can compute the derivative of this function. May not be possible. You may not be able to solve this equation. Okay, so some of you, I'm sure you've studied the Newton-Raphson method. Even I studied that at school. I'm sure you did that. So there is a numerical method for root finding. Then, of course, you have to be able to compute the Hessian matrix, and for us, the second derivative. Okay. But I'm not asking you, of course, you never have to do this in practice for theory. It's not even in your tutorial questions, so you don't have to worry about this. But I'm just showing you that this random sample concept is important. Okay, let's have a look at some examples before we go back to the regular next lecture notes. We're not going to go too far today. You might notice my voice is gone because I have just got off a long flight. So I think it's right 6 a.m. in the morning. I was just in Europe, so we may finish a little early if it's best start to lose my voice. Okay, anyway, let's have a look at an example. So here's an example of calculating the maximum likelihood estimator when you have Poisson random variables. So the idea is that you assume that you have a random variable of interest, for example, that counts of something that you have seen before. So if you remember, I think back in chapter 4, we studied the Poisson distribution, and there were many cases where we're interested in calculating probabilities associated to the Poisson. But we don't, in many cases, we don't even know what the associated parameter is of the statistical model. Okay, so what we're going to do here is to use this maximum likelihood estimation procedure to precisely calculate lambda, and that's the lambda which is most consistent with the data. So this is called the MLE's maximum likelihood. Okay. So our parameter theta lambda is exchangeable, so we're going to use lambda here. Okay, and it's very simple. We've just got this simple algorithm following points 1, 2, 3, and 4, and that's what we're going to do. So what's the likelihood function? The likelihood function is the joint density of the observations that we have seen under the parameter value lambda for any fixed lambda. And remember, we're assuming a random sample. So if you have a random sample, the joint density of the observations is just the product from I is 1 to n of the density function for the random variable of interest evaluated at the data. Okay, so this is a function where I know the x's but I don't know the lambdas. Okay, and so then there's a simple calculation. Well, basically, this function e to the power minus lambdas is multiplied by itself n times, so that gets e to the minus lambda n. Then this product I is 1 to n of 1 over xi factorial, I get that. And then I get lambda to the xi, and I get the product of those. So that's lambda to the power of x1 times lambda to the power of x2 times lambda to the power of x3, dot, dot, dot. So that's lambda to the power of the sum I is 1 to n of the xi's. Okay, so that's my likelihood function, and all I need to do now is to maximize this function with respect to lambda. So the way in which we proceed, remember, we take a natural logarithm. So I just tend to take a natural logarithm, a natural logarithm of this function. So if I take a natural logarithm of this function, what am I going to get? Well, remember, the logarithm is the sum of the logs so the logarithm of a product is the sum of the logs. So I think about this one first. So the logarithm of e to the minus n lambda is minus n lambda. Okay, this is the reason why we'd use natural logs. We get lots of exponentials in statistics, that's why. Okay, minus n lambda. The logarithm of this is the sum I is 1 to n of the logarithm of lambda minus, and then this thing. We don't somehow care about this thing because you can see it's not a function of the underlying parameter. Okay, so now we have a function in lambda. We now need to optimize this with respect to lambda, so we're going to differentiate this function with respect to lambda, and then we're going to solve. Okay, so the gradient vector, as I said, is just a derivative, so I'm just differentiating this function with respect to lambda. So the derivative of this with respect to lambda is minus n. The derivative of this with respect to lambda, the sum of the xi's over lambda, and this one is a constant lambda, so it is the derivative 0. So what do I want to do now? I want to solve the equation that this right-hand side of the equation is equal to 0. Okay, or if there exists a root, I mean, it puts chance where there's a maximum likelihood estimator. So I want to solve the equation minus n plus 1 upon lambda times the sum of the xi's is equal to 0. Okay, so you can rearrange this function. You can put the n to the other side, and then you're basically going to get lambda is 1 over n times the sum I is equal to 1 to the xi's. Okay. Now, before we go any further, this is kind of looking quite useful. Why does it look quite useful? Well, remember what is the value of lambda. The expected value of a Poisson random variable is precisely lambda. Okay. Now, the highlighted equation on the right-hand side is the mean of the data. So remember, the mean of the data is just the average. Okay, the average, I take all the numbers up and divide by n. That's my mean. So what this says is that a possible estimator which maximizes the likelihood is the mean of the data with respect to lambda. Okay. Now, we don't know yet whether or not it's a solution, but we can work it out whether it's an MLE. So now if you differentiate this function, excuse me, this feedback is annoying. I want to differentiate this function on the right-hand side with respect to lambda one more time. So obviously minus n goes, and I get minus 1 over lambda squared times the sum of the xi's. Okay, so now this function, the second derivative, right, whatever lambda is negative, right? So basically this thing is basically a maximizer of the log likelihood or log likelihood function. They're exchangeable in this case. So that is the case. Of course, you have to observe at least one data point bigger than 0, but I think that's a complication you don't care about. So the maximum likelihood estimator of the parameter lambda is the mean of the data. And it's good, it makes sense in some sense for us because the mean of the data is exactly equal to, so the estimate of the mean of the random variable is equal to the mean of the data. Okay, and that's how you estimate it. One way to estimate lambda. Okay, so we've reached our break time, so we'll break for 5 minutes, and then we'll return with one more example, and then we'll go back to our lecture notes. So we resume at 14:50. Resume for the second example, just another example. It actually fits very well with the rest of the lecture notes. So in this example, I'm going to take a finite sample, random sample, from a random variable which is exponentially distributed with lambda. So again, this is just a different notation. It doesn't matter too much. So remember that the PDF of an exponential distribution is a random variable which is continuous, and if it has parameter lambda, then basically the density function is lambda e to the minus lambda x. Okay. So in this case, what we want to do again is to compute the maximum likelihood estimate of theta, which is lambda. They're the same thing. And what we're going to do is observe these random variables x1 up to xn. Okay, so the joint PDF of the observations, remember, for a given lambda, that's just equal. So they're assuming their IID, independent identically distributed. So the product I is 1 to n. And this is just the density function of a given data point for the parameter lambda, which we wish to estimate. Okay, and so now in this case, lambda appears n times, right? We get lambda times lambda times lambda times lambda, so I get lambda to the power n, and I have e to the minus lambda x1 minus multiplied by e to the minus lambda x2 multiplied by e to the minus lambda x3, so on and so forth, which is the same as e to the power minus lambda times the sum I is 1 to n of the xi's. Okay, so this is the joint density function of the observations. Now our second step of the algorithm to compute the maximum likelihood estimate is to compute the natural logarithm of this function and differentiate with respect to the parameter lambda. So the log likelihood function, the logarithm of this function, so the logarithm of this is n log lambda, and I get plus minus lambda to the sum times the sum I is 1 to n of the xi's. Okay, it's just simply computing the sum. So the logarithm, natural logarithm. Okay, and so now what we're going to do, we have to work out what is the derivative of this function with respect to lambda. So that's going to be, so the first part on that highlighted equation is n over lambda. That's the derivative of n times log lambda. And this derivative is minus the sum I is 1 to n of the xi's. Okay, so now what we want to do, we're going to solve this equation equal to 0 with respect to lambda. So if I do that, so what I want to do is to solve this equation with respect to lambda. And if I do that, it's very simple to show that lambda n, the possible MLE, is like that. Okay. Now, why would this be a potentially useful estimate? Remember that if you have a random variable x, which is exponentially distributed with parameter lambda, that the mean of the random variable is 1 over lambda. So what this estimator proposes, potential estimator proposes, is that the mean of the 1 over the mean of the data is equal to lambda. So again, lambda is 1 over the mean of the data is 1 over lambda. So 1 over lambda is the mean of the data. Okay, there's a natural interpretation in terms of the intrinsic underlying expectation of the associated random variable. Okay, but we still don't know whether or not this function, this potential solution to our derivative equation is exactly a maxima. So we want to differentiate this function with respect to lambda. So this is minus n over lambda squared. Okay, and so long as this function, this thing is bigger than 0, okay, so we have to observe a data point which is not 0, and of course the chance I see at 0 is very, very low. All of them 0. So basically this is our maximum likelihood estimator, and again it has a natural interpretation. So the mean of the random variables, the mean of the random variables is 1 over lambda, so the estimate of the lambda is 1 over the mean of the data. Okay, and this is the most likely value that we are going to see for our joint data model for the associated parameter. Okay, so this is just an application. All this has been, just to again keep in mind, is just an application of where you use this. Now we're going to see this in more I think more simplistic terms, but less practical terms in the rest of this lecture notes. Okay, so let's return ourselves to the main lecture notes. So we've got to page 22. And what we're going to do is look at the sampling distribution of the sample mean. Okay. Now, hopefully, that makes sense of why this is interesting, right? Because you saw in our two examples, okay, that it so turns out that the sample mean, which is a function of the data, played an intrinsic role in trying to estimate our parameters. And in general, this is the case in many scenarios. Okay. So here you go. So this is what it says. So our main purpose in selecting random samples is to elicit information about unknown population parameters. Okay, that's exactly what we just did in our additional lecture notes. So for instance, you might want to know the proportion of people in Singapore who prefer a certain brand of coffee. Well, I don't know why you don't want to know that, but I guess a marketing company might. Now, in practice, one can think of the proportion of people who prefer a certain brand of coffee. The sample of the size of Singapore, the population is approximately 5 million people. You wouldn't be able to, I don't know, maybe it's only probably 4 million are actual consumers. But the key point is that no marketing company is going to interview every single person in Singapore to try and find out the information. You know, you're not going to survey 4 million people and say, do you have brand X every day or something? You're just not going to do that. So you're going to take a random sample. Okay, so basically a large random sample is selected from the population. So let's say that people between 18 to 40 drink a lot of coffee, although I think maybe it might be a bit older, 18 to 50 maybe drink a lot of coffee. And so basically you take a random sample from this age group, and then you form your sample upon this basis, and then you can estimate the proportion in Singapore which actually have this certain type of brand X coffee. Okay, so now this value is being used to make some inference concerning the true population. So if, for example, 10% of people are having brand X, then this might be quite a significant market share in Singapore. So you might try and extend your coffee production or range of values of coffee in Singapore, and so on and so forth. That's what it means. So inference means to try to make some, for example, some decision associated to the random variable of interest. Okay, so the value that you've computed from this sample is called a statistic. Okay, so we've already seen this. You should know. I'm sure you don't have to tell you that the mean of the data. This is exactly the mean of the data. Is a statistic. It's essentially at our level, it's just a function of the data. Okay, which summarizes it, hopefully in some meaningful way. In this case, the average is a meaningful statistic, and I'm sure you know many others, such as the median and the mode, and so on and so forth. Okay. Right, so since many random samples are possible, so remember that the mean of the data is only associated to the thing that I actually see. Okay. So many random samples are possible. So that what that means is that basically the statistic will vary. So if I take let's say I take 100 samples of individuals, then the mean will not be the same for those 100 samples of 100 individuals, 100 random samples. There's very little chance of that unless you're measuring some sort of discrete or categorical variable. Okay. So basically the statistic is itself random. Okay, and it is meaningful and it is useful, as we're going to see in a moment, to consider the probabilistic distribution associated to a statistic. Okay, and the distribution of such a statistic is called the sampling distribution. So that hopefully these things are all clear. What we're talking about is that, for example, here, remember this is the mean. Okay, this is the mean from given realization of data. right? But of course I could get a different sample and another different sample. So if I treat this function as a random function of IID random variables, and I ask myself what is the distribution of that, that's called the sampling distribution. Okay, that's precisely what this red text says here. Okay, let's see an example. So the example is the sample mean. Okay, so this, so hopefully those loads that I showed you, which are non-examinable but still, I think, very interesting, exemplify why the sample mean is so interesting or important in practicality. Okay, there are of course many problems of using the sample mean, but we won't talk about those right now. So if you have x1 up to xn, it's a random sample, so all that means is IID sequence of random variables, okay, of size little n. Then the sample mean is just the average of those random variables. So notice the difference in notation. So here again, remember, I can't highlight it, these xi's are random variables. In these notes here, these xi's are observations, so they're used, I use lowercase. So we always use lowercase for realized things and uppercase for random things. Okay, so that's why I was using little x's here, whereas this is why my colleague was using big x's here. Okay, and we've seen, I've told you about that convention before, but anyway. Okay, let's study this a little bit. This is kind of hopefully it will exemplify what I've been talking about just on the previous slide. So suppose what we want to do is to study the sampling distribution of a sample mean where we have a discrete uniform population. Okay, so here what we have is a population size capital N is 5. Okay, and basically the probability that I take the value 3 is 1 over 5. The probability I take 5 is 1 over 5. The probability I take 11 is 1 over 5. Excuse me. So this is the sample. This is the probability mass function for this sequence, for this given random variable. Okay, this is the population, if you like. Okay. Now the mean of this random variable, well, we've done that a few times. The mean of the random variable, which has this notation E of x, is just the sum over all possible values of x of little x times the probability mass function. Now the probability mass function is 1 over 5 for x in the set 3, 5, 7, 9, 11. So the expectation is 1 over 5 times 3 plus 5 plus 7 plus 9 plus 11. Apparently that gives you the value 7. You're going to see where we're going with this in a moment. Okay, we can also compute the variance. The variance is just the expected value of x minus its expectation all squared. So that is to say, it's the sum over all x values of x minus mu of x, the expectation of x squared, times the probability mass function. Okay, so mu of x, we computed it was 7. F of x is always 1 over 5. So this summation just becomes 3 minus 7 all squared, that's the first value of x, plus 5 minus 7 all squared, that's the second value of x, and then the fifth value of x is 11 minus 7 squared, and you add all the ones in between. So the variance of the population is 8. Okay, not very, hopefully that's relatively understandable given what we've studied in the last 5-6 weeks. Okay, now suppose we list all the possible sample sizes, samples of size 2 with replacement, and then for each sample we compute the mean. Okay, so it's with replacement, so basically what I've got is I've got these numbers, so that I can pick a 3, I can put it back, I could pick a 5, and then my sample is 3, 5, or I can pick a 9, and I can pick a 7, or I can pick a 9 and a 9, and so on and so forth. So in this scenario, basically, so these are the 5 squared possible samples. Okay, so remember this is capital N to the little n. So capital N is 5, little n is 2. There's 5 squared possible samples. So the sample mean, is just going to be this number plus this number over 2. So for example, if I go here, 7 plus 9 is 16, 16 over 2 is 8. If I go here, 9 plus 5 is 14, 14 over 2 is 7, and so forth. 11 plus 11 over 2 is 11. Okay, so this is just a summary of all possible 25 samples and their associated sample mean. Okay. Now what's the point here? Well, the sampling distribution of x bar can be now found, right? Because x bar has a certain number of values, right? So x bar could be 3. Now, when could it be 3? It can only be the case where we get a 3 and a 3. Now, what's the probability of getting a 3 and a 3? Well, I choose 3 with probability 1 over 5, and independently I've chosen the other 3 with probability 1 over 5. So the chance of getting a sample mean of 3 is 1 over 5 times 1 over 5 is 1 over 25. Okay? Now you can take the case 4, just to show you, I just want to show you how you have two cases. So you have this one and you have this one. Okay? So similarly to the case before, the chance of getting 3 and 5, so the mean of 4, is 1 over 5 times 1 over 5. So the chance of getting this entry is 1 over 25. The chance of getting this entry is also 1 over 25. And these two events are mutually exclusive, so the probability of their union is the sum of their probabilities. So the chance I get a mean of 4 is 2 over 25. Okay, and similarly you can do this for all the others, right? So you can take the case 10. So the case 10 is where you have this one and this one. You get 11 and 9 or 9 and 11, and both of those have means of 10. Okay, and both of them have probability 1 over 25 of occurring, so the chance of getting a mean of 10 is 2 over 25. Okay, hopefully that's relatively clear. Okay, so what have we done here? What we've derived is the sampling distribution of the mean of two of these numbers. We're going to see why that's important in a moment. Okay, so this is the sampling distribution of x bar, and we can compute the mean of x bar. Okay, so and this is pretty straightforward to compute, but if you want, the mean of x bar is just the sum over all possible values of, actually this should be x bar, not x, by the way, x bar times the probability mass function of x bar. All you have to do to compute the mean is you do 3 times 1 over 25 plus 4 times 2 over 25 plus 5 times 3 over 25 plus ... plus 11 times 1 over 25. Okay, that's what you get, and you get 7. Okay, and you should recognize that number if you've been listening to me, because that was actually the mean of the random variable x, actually. Okay, now the expected value of x bar squared, you can easily compute that as well, because basically all you have to do is you square this number and multiply it by the probability mass function. So in order to, what am I doing here? I'm trying to calculate the variance. So in order to calculate the variance, I compute this one squared times the mass function. So basically to calculate this number 53, what I do is I do 3 squared times 1 over 25 plus 4 squared times 2 over 25 plus ... plus 11 squared times 1 over 25. And apparently that's 53. So the variance of this mean, well, that's equal to the expectation of the square of the random variable, 53, minus the square of this one, which is 49, and then you get back 4. Okay. Now, in this example, what we have seen is that the sampling distribution, we know the sampling distribution, we also know the mean of the sampling distribution for the mean is 7, and we also know the variance for the sampling distribution, which happens to be 4 over 2, which is 8 over 2. The sample mean was 8, variance was so the population variance. So in this scenario, basically we've seemingly got a relationship between the mean of the population and the mean of the mean. This is not perhaps this is the expectation of the mean of the random variable, and this is the variance of the mean of the random variable, and seems to be intrinsically linked to the variance of the associated random variable. And that's exactly the case. Okay, so we have this theorem, which I will give you a proof of. I could do it on the board, but I don't think it's going to show up okay. Well, we'll go up to, okay. So we're going to go up to page 36, not because I'm a specialist of these things, but I think it's better that we go a little bit slowly. And also I want to prove this theorem, which I will do for you tomorrow. So the theorem is like this. So you have a random sample of size n. So you have a sequence of random variables, x1, x2, up to xn. They're independent and identically distributed, and they have the same distribution as the population. Okay. Now we take that from an infinite or finite population, okay, with replacement. Okay, and we have a population mean mu and a population standard deviation sigma. So what that means is that the associated population distribution has a finite mean and a finite variance. Not always the case, actually. And what we are going to do is we're going to relate the distribution or the moments of the mean of the random sample to the mean of the population, and the standard deviation or variance of the mean to the variance of the population. So the sampling distribution for a sample mean x bar has a mean and a standard deviation, and it looks like this. So the mean of the mean, okay, this is just equal to the average value, and the variance of the mean is just the variance over little n. Okay, that is to say that the expected value of x bar is equal to the expected value of x, and the variance of x bar is the variance over n. It's very simple to show this result. I'm going to give you a proper result now, but just if in case you're wondering why it's true, I know you can't read this, and if you're on video you have no chance to read it. But let me just show you why this one is true. It's just 2 lines. So you want to compute, I'm writing this as big as I can, the expectation of x bar. Okay, and you want to show it's equal to the expected. Don't worry, you don't have to copy this down. I will put it in a printout tomorrow. So this is equal to what? The expectation, I'm using this notation, and this is 1 over little n times the sum I is equal 1 to little n of xi's. Okay, so this is by definition, right? And what I want to do is I want to derive this result, okay? And I'm told 2 things. I'm told that xi's are independent and they're identically distributed. So it's very simple to work with the right-hand side of this equation. So first of all, 1 over n is a constant, so I can take it outside my expectation. And we know the sum of random variables. If I take the expectation of sum of random variables, that's the sum of the expectations. So that's equal to 1 over little n times the sum I is equal 1 to little n of the expectation of xi. Okay, and again, I know if you're right at the back, you have no chance to read this, but basically the expectation that the sample mean is equal to this average of the means. Okay, this is true for any sequence of random variables x1 up to xn, but now we know something about this xi, because this xi happens to be they have the same distribution. So this expectation is the same for each I, and we know what this expectation is. Okay, this is what we're told this at the beginning. The population mean is mu. So what this thing is on the right-hand side, I'm sorry, you probably can't see it. So this thing is equal to 1 over n times the sum. I is equal 1 to n of mu, and that's equal to n times mu over n, which is equal to mu. Okay, I'll write it down on a piece of, I will print this, I'll do it on a computer for you tomorrow, so you don't need to copy it down. But hopefully it's clear that you can see, basically we saw very similar results, remember when we were looking at the binomial distribution, because there we also studied sums of random variables, and it so happens that that we can do that very easily here. Okay, the variance also is very similar, because basically the variance of a sum of independent random variables is the sum of the variances. Okay, I am fairly certain I told you that. There's a reason why we're not proving them. These proofs are not examinable because the calculations are not here nor there. But this is the final result. Okay. Okay, and I will put the proof down for you. We'll go through it at the start of tomorrow's lecture. Okay, so our last part of today's lecture. We will see the example. It'll be very interesting for me to just do that. Okay, it's something called the law of large numbers. Okay, so this is very important. Why is it very important? Well, it's important for many reasons. For us, it's interesting because basically it's a good way to estimate the mean of a population. Okay, so what does it say? It says I take x1, x2 up to xn is a random sample of size n from a population which has a mean mu. You don't need it. Yeah, I mean, you don't need a finite variance actually. But anyway, let's suppose you have a finite variance. Okay, this is called the weak law of large numbers. It's a classical result in probability theory. And what does it say? Well, the result says if I consider the probability, so I take for any epsilon, yeah, I mean, typically you take R epsilon bigger than 0 because it doesn't, the statement obviously is vacuous if epsilon is negative. But what does this statement say here, or what does this thing mean? Well, this says that the probability that the difference between the observational, the random mean, the sum of the xi's over n, take away the mean of the population, and this is the chance that is bigger than epsilon. Okay. So what we're interested in, so we fix epsilon is positive, and I'm interested in the chance, basically the chance that x bar is different from mu. Okay. And what this result says is if I take the limit as little n goes to infinity, so I get more and more random members of my random sample, then basically the chance that the sum of my random variables divided by n is different from my population mean is essentially 0. This is actually something that's classical in probability theory, which you don't need to know, but if you might be interested, it's called convergence in probability. In fact, there's even a strong, with the finite variance, you have an even stronger statement than this, but you don't need the finite variance. Okay, so this is true for all epsilon. You may as well say epsilon is positive, because if epsilon is 0 or less than 0, then obviously this statement is trivial. Okay, if again, so epsilon you could say is for all epsilon greater 0. Okay. So this means, just if you want, what does this statement mean? So formally in mathematics, again, you can take it how you like it. I've given you the interpretation, what it means. If you don't like the statement there, I'm writing things on the board because this stuff are some things that I don't know very well, and actually I find very interesting. But again, what this statement means, just from a probabilistic perspective or a mathematical statement, is the limit as little n goes to infinity of the probability that x bar minus mu is greater than epsilon is equal to 0 for all epsilon positive. Okay. If you prefer this as a statement, I don't know if you can read it in the back, but anyway, it's not important because it's written for you right there. Okay, so it's equivalently this, and what it means is that as you get more and more individuals in your random sample, your sample mean is basically almost the same as your population mean. Okay, so for example, if you're interested in estimating your population mean, well, you could just have a really large sample, and then your population mean is essentially the same as your mean of your data. Okay, so to say a little bit more, well, this is what it says here, but so you see the significance of this if we return to our example for the Poisson. Remember, in the Poisson case, what we were doing, we were estimating the parameter lambda. And remember that the parameter lambda is the mean of the random variable. Okay, so what the statement that we've just learned means is that in this case, this is the mean of the data. Okay, so if n here, the number of data points, is extremely large, then basically this thing, which I've highlighted on the right, is almost the same, or very similar to the true value of lambda, which I don't know, but I want to estimate. Okay, this is the interpretation of that result, which is, like I say, it's called the weak law of large numbers. It's true, actually, there's a stronger version of it. So again, the remark, which I think is particularly relevant here, it says, so again, just in words one more time, it says that the sample size of the number of, so the number of data points, the size of the random sample gets bigger and bigger. The chance that we have a difference between the sample mean and the population mean is basically negligible. Right? I mean, this is an interpretation. This remark is not a clean mathematical statement. It's not true, but it's a way to think of what does it mean. Okay, that's what it means empirically, but it's not really what it means mathematically. This is the exact definition if you like mathematics. Okay, let's see this example, and I think we will stop, especially since I'm beginning to fall asleep. Okay, so here is an example. We take x1 up to x little n. It's a random sample from the uniform distribution on 0, 1. So remember, that's a PDF, which is taking the value 1 if x lies between 0 and 1, and otherwise it takes the value 0. Okay, now you can remember, hopefully, from last last week, the last chapter, that the expectation of a uniform random variable on 0, 1 is 1 over 2. Remember, if of uniform A, B, the mean is A plus B over 2. A is 0, B is 1, 1 plus 0 is 1, 1 over 2 is the mean. The variance has a different formula, is 1 over 12. Okay. Now, suppose that we have a sample size which is 3 times 10 to the power 6, so 3 million points. And I take epsilon is equal to 0.001. Okay, so 10, very small. So now xn bar is the sample mean from this sample size. So we know already that the expected value of x bar, well, our result says exactly what it is. The expected value of x bar is equal to the true value of the sampling mean population. So xn bar is equal, the expected value of x bar is 1 over 2, and the variance, remember, is the variance over the size of the sample size, sigma squared over n. Okay? Okay, so now consider the probability that the difference between the mean of my sample and the true value of the mean is bigger than epsilon. Okay, right, epsilon is 0.0001. So what we want to do, what does this say? So find a k such that k is equal, we're going to use a Chebyshev inequality. So have you remembered the Chebyshev inequality? Which chapter was that? I forgot that. We just want to remind you what the Chebyshev is, but I really forget which chapter it was in. Chapter 2. Yeah. There we are. So I just want to remind you what Chebyshev's inequality is. So remember what Chebyshev's inequality is. So let x is a random variable which has a finite mean and variance. Then for any positive number k, we can show that the probability that x minus mu is bigger than k, sigma is upper bounded by 1 over k squared. Okay, I'm reminding you of this because we're using Chebyshev inequality. Okay. Okay, so now the reason why he's using k times the square root of the variance of x should be clear, because what he wants to do is he wants to apply this inequality. Okay, now in our scenario, the random variable x is playing the role by our sample mean. Mu, remember, that's the expectation of the random variable. We know that the expectation of the mean, the expectation of the mean is 1 over 2. Okay, so I now want to find the probability that the absolute difference between the sample mean and its true mean is bigger than k times sigma, right, then that's upper bounded by 1 over k squared. So what he's trying to do is he's trying to find k times sigma is equal to 0.001, which is my epsilon, or our epsilon, excuse me. That's what he's doing. Hopefully that you can understand that basically he's using this equality. Sigma is the variance of the mean, which is sigma squared over n, and k is a number. So we want to find k such that k times the square root of the variance of the mean is 0.001. Okay, so that is to say that k is divided by 0.001 by the square root of the variance of x bar. The variance of x bar is 1 over 2 times 3 times 10 to the 6. So basically k is apparently 6. Okay, so now the probability that xn bar is bigger, minus 0.5 and the absolute value is bigger than 0.01 is the probability that xn bar minus 0.5 is bigger than 6 over the square root of the variance of x bar. So now Chebyshev's inequality tells that this quantity is precisely upper bounded by 1 over k squared. Okay, k is 6, so this thing is upper bounded by 1 over 36 is 0.02778. This is small. Okay, relatively small. And you can imagine now, if I made n much, much bigger than 10 to the 3 times 10 to the power 6, right, then this one, the variance of x bar, gets smaller. So basically what that means is that k times the square root of the variance of x is equal to the same value of epsilon. Well, k will get much, much bigger, and so this upper bound will get much smaller. And so basically, as I allow n to get really, really big, the Chebyshev's inequality is going to say that this thing gets arbitrarily small, whatever, for any positive epsilon you choose. Okay, and so what that means is this is just a verification that indeed, as you get more and more, the random sample gets larger and larger, so the sample mean becomes exactly the population mean. Okay, and that's the point of the example. You can, in fact, yeah. I mean, there's other ways you can do it. Chebyshev's inequality is there's not very sharp in this example, actually. There is a better inequality to use, but it's not important. Okay, right. Well, we have time. I'm just going to tell you what we're going to do. I don't want to get too far ahead of ourselves because, as I said, tomorrow I want to just give you this result here. So just to tell you before we go any further, we're going to discuss the central limit theorem, which is kind of the, I guess many people think it's one of the kind of fundamental results in statistics. I mean, it's a very important result in probability theory is what it is. It's not really a statistical result. And what it basically tells you is that the sample mean, when you appropriately scale it and center it, it becomes Gaussian, irrespective of the underlying distribution of the associated random variables. So what am I saying here? So you note that in this law of large numbers, right, I have not assumed almost nothing about the associated random variables, only that they have finite means and variances. I don't think you don't need the variance at all, actually. So there is no distributional assumption about the xi's other than this point. The central limit theorem is very similar. It's exactly the same context. And it says that basically this quantity, when you are appropriately centered and scaled, is Gaussian. And so what that means is that underlying basically everything one does in statistics, if the number of samples, little n, the size of a random sample is rather large, then essentially you're getting a Gaussian or normal distribution type behavior, which basically tells you why the Gaussian distribution is so prevalent in terms of doing probabilistic calculations. Okay, why you use it for hypothesis testing, why you use it for many other things. Okay, we will explain this result explicitly tomorrow, but before we do that, I will go through this result tomorrow as well. Okay, so I think that's we're kind of well ahead of the other two groups. So that's it for today. Thanks very much for your attention. Just remember, don't forget that the midterms on Tuesday. You have all the details for that. It should be of the same standard as last semester's midterm. Thank you.